Here we go. Here we go. Here we go. Here we go. Here we go.
Hey everyone, welcome back. I think we may still be having some issues on the LinkedIn live side, but if you are catching this on LinkedIn, you can go over to twitch.tv/AWS to catch the action there. It seems the stream has been going strong on that side. Technical complications aside, we are very excited to have this session here. Joining us to talk a little bit about Amazon Braket is Martin Schuetz, research scientist from the Amazon Quantum Solutions Lab. Martin, thank you so much for taking the time to talk to us about Braket today. This is something that's very exciting for us, and I know a lot of the folks at home.
My pleasure. Thanks for having me.
Yeah, so quantum computing. Wow, this is I said at the top of the show that we've covered all walks of life, or many walks of life here in the technology space, but quantum computing, this is certainly a first. So I am by no means the foremost expert, nor am I a research scientist at the Quantum Solutions Lab, so I figured I'd throw it over to you. In a nutshell, could you describe what quantum computing is?
Right. So the basic idea behind quantum computing is to leverage the intricate physical laws of the microscopic world, and that is, in a nutshell, quantum mechanics, to do computations in a new and improved form. So these quantum mechanical laws, they may seem very bizarre to us because we don't experience them in our everyday life, but they have been tested and verified again and again over the last years and even decades, and have helped us building up confidence in this theory, such that now we're actually ready to build a machine that unlocks these very laws. And we are very excited because, as it turns out, this machine holds the promise to provide speed ups to very hard and relevant problems, even some problems that could not be solved otherwise. So it really opens up the door to a new paradigm in computing. But before closing here my intro statement, there's one important catch that is important to make here. There's a lot of hype around quantum computing, but really I want to be clear that this technology is in its infancy. It's really early days for quantum computing, simply because there are major scientific and engineering challenges ahead of us. Still, we think it's the right time for our customers to get access to quantum computing and start exploring and experiment the beautiful world of quantum computing.
Yeah, awesome intro. I'm personally very curious. I mean, I've heard a lot of buzz around quantum computing, seen some interesting academic work that then later had to be retracted. But so it's great to have an expert like you on the show with us. Could you briefly explain the fundamentals of quantum computing? You alluded to quantum mechanics, but can you take us a little bit deeper on that?
Sure. Let me try to use the following picture. So you see, at the very fundamental level, all our so-called classical compute, from your cell phone over your laptop to even the most powerful supercomputers today, they process information in a binary form, typically identified as zeros and ones. But that's just a convention. You could also call them mom and dad, but you could also call them North Pole and South Pole. So in essence, what you have with a classical machine is, so somewhat of a compass needle that can point either to the North Pole or to the South Pole. That's a classical bit. A quantum computer operates with a quantum mechanical bit, in short, a qubit. And what a qubit can do, it's a compass needle that can not only point to the North Pole or the South Pole, but it really can point anywhere on the globe. And that is it's basically a hybrid between North Pole and South Pole. It's what we call a superposition.
This is bringing me back to some of the math and engineering I did when I was in school. But with the globe example here, right, you have sort of north and south poles, but then the ability to represent sort of the quantum state, I guess, or wherever that needle is pointing on the world. Not only it's a continuous plane, I'd imagine, right? So there's
Yes.
There's a very large number, if not infinitesimal number of values, I guess, in theory, it could hold. But then you could also represent that with something like polar coordinates in this scenario, right? Where you have like the rho, the radius, and
that's right. Yeah,
theta
lives
or
on a
whatever.
sphere, spherical coordinates. Yeah.
Yeah. Cool stuff. So That was quantum computing 101 in 5 minutes. Thank you everyone for tuning in. But in all seriousness, it does lend a bit more weight to and understanding to sort of the computer that will then operate on those underlying mechanics, and how sort of the codification and information is fundamentally different, right? We're not talking about something that's slightly more efficient than systems that have existed before. This is building entire systems and technology and computers and in Braket APIs and ways to interact with those for a fundamentally different paradigm. And I know the word paradigm gets thrown around a lot. Maybe it's apt in many of the scenarios it is used. I think there is no more apt scenario about talking about a new paradigm than quantum computing.
Yeah, absolutely. This is really interesting. I mean, but I'm wondering, if you're talking about quantum computing being such a paradigm shift that at the bit level, you're talking about a qubit, which fundamentally behaves differently from a classical bit. Mm-hmm. How does that percolate up the stack? And I'm curious about all aspects, but maybe we definitely won't have time to cover all the implications of quantum computing from scratch. But maybe you can kind of jump ahead in the queue and just tell us, like, how do you program a quantum computer? Like, what does a quantum algorithm look like?
Right. Let me actually let me share the screen, because I will pull up a little slide here to visualize this. So at its core, it's actually not so different from classical computers, which operate with Boolean circuits, right? Where essentially you can build more sophisticated, more advanced functions with core simple building blocks. So for example, here you have a function that I call Q. It's A times B. A and B are classical bits here. And I have stacked together these core building blocks in some circuit level fashion to come up with this more sophisticated function that I want to generate here. Quantum circuits are not that different. You see, the input are not bits, classical bits, but these qubits, typically drawn identified with lines here. So here we initialize 3 qubits, all pointing to the North Pole. And now we use quantum gates. These are our core building blocks. It's really like playing a little bit like Lego. Now you stack together these core building blocks, what we call, for example, here a Hadamard gate applied to the first qubit, a Hadamard gate applied to the second qubit. These are single qubit gates because they operate at 1 qubit at a time. We also have, in our arsenal of Lego, 2 qubit gates. Like this is what we call typically a CNOT gate. And what you figure out is by stacking these building blocks together here, starting from a very simple quantum state 0, 0, 0, you come up with a maximally entangled state where all the qubits are actually either pointing to the North Pole, 0, 0, 0, or pointing to the South Pole. So you have a new quantum state stacked together that's how we build quantum circuits using core building blocks.
That is fascinating. May I ask, when you say that there's this gate that operates on a single qubit, mm-hmm. At the hardware level, what is that? I mean, because when you show the classical circuit on the left, that looks familiar to me, right? I can see that, okay, well, that's an AND gate, that's an OR gate, this is a transistor, this is whatever. Like, we know how to build that. Mm-hmm. But if I were to put the H, I don't know, I forget what you call that, the H.
It's the Hadamard gate.
Hadamard gate?
It's the Hadamard gate. Essentially what it does, it takes your compass needle pointing to the North Pole and tips it into the on this hemisphere here. So in a superposition between equal superposition of North and South Pole.
Okay.
But coming back to your question, what this means, obviously now this abstracts away the physical implementation of this machine, right? The circuit level. So there are different technologies available. I will show some of them in my demo later on. And it depends on what implementation you use. At this point, we make available to our customers superconducting chips. In that case, this gate here corresponds to a microwave pulse applied to a superconducting qubit. We also make available trapped ions. These are really single ions, so charged atoms trapped in vacuum. and you shine. Essentially what you do is to implement the Hadamard gate is, for example, you shine in laser light pointing at the single qubit.
This is fascinating.
This is so cool. I mean, and it's so different from what, I mean, because the transistor, I mean, we know those pretty well, right? I mean, but this is so different, even at the fundamental building block level. This is fascinating.
Yeah, I mean, like even looking at like on the Boolean circuit, you have a given value, it accepts one or two. Like even just the idea of a qubit and like from what I understand about like stats and chemistry that I've learned, you sort of have like this probability density function over sort of like how likely a qubit is to be in a certain state at certain times, or like the likelihood of each state that it could possibly be in. And then the Hadamard gate almost acts like in AI and machine learning, a lot of the breakthroughs with things like neural nets were involved the construction of these layers that would take your input and then apply basically like a sinusoidal curve to it to either push it into like either the 1 or a 0. And that sounds kind of similar to what the Hadamard gate does here with sort of the quantum state. It's and again, I don't know.
I will actually, in my demo, there are very interesting emerging similarities between deep neural networks and some of the more modern advanced quantum algorithms circuits. I'm going to cover this in our demo.
Okay, just one last question. I know this is because this is just so fascinating. One more question, and I promise we can get back on track. What would happen if I took a qubit and I passed it through 2 Hadamard gate in series?
You are back. You are back to where you started from. So you essentially, let me think. You have a Hadamard gate that brings you from 0 to 1, and into this hemisphere here, and another one brings you to the South Pole, basically. So in a classical state again.
So 2 Hadamard gates in series inverts the qubit. Is that?
Yes. That.
Or is invert even applicable in this?
Yeah, sure. You can. I mean, you can stack together whatever you want.
Okay. This is a whole new world for me. So let's keep going.
Cool. So tying this all sort of, back together, we started at the top, intro to quantum computing. I know we've weaved in now here the comparison to classical systems and, classical circuits, the computers that power them, the logic and sort of the programming that we would use to build on those systems. I know, Martin, you mentioned sort of before the show that you would show us a little about what that looks like. But before we get to that, we haven't really spoken a lot about Braket in particular. So with all of this quantum computing sort of foundation in front of us now, how does Braket sort of fit into this landscape? And what did we launch? Because Braket has gone generally available this week.
Right. So Amazon Braket is a fully managed service for quantum computing. So really what we want to provide to our customers is one-stop shop development environment that gives you all the quantum computing tools and technologies into the hands of our customers. It is fully integrated into the AWS cloud and gives you full functionality to design quantum circuits, quantum algorithms to test them against high-performant classical simulators, and then eventually run them on your choice of actual quantum computers, where we offer different technologies. So really what we want to create with Braket is offer sort of a level playing field for quantum computing and take away all the undifferentiated heavy lifting behind quantum computing.
He said it, not me. It doesn't count.
That's right.
No, but that's it's great to hear. I know Rob rips on me when I said it, but I'm clearly not the only one who's barking up that tree, right? No one likes doing work that is.
Your fingerprints are all over this. I blame you, Nick.
Yeah. I what's the word in courts, right? You tainted the witness or something, right? It's no, but I promise I did not entice Martin to say that. But again, there are enough complexities with running classical systems. I can't imagine wanting to inherit the large number of challenges to running a quantum computer. So being able to have managed service lets me experiment on that and not have to worry about that. Sounds quite enticing to me. So You said, Martin, that you would show off a demo. I hope
Yep.
I'm not signing you up for something that you aren't ready for, but is there any way we'd be able to see Braket today and give folks a chance of what it looks like to use?
Yeah, absolutely. Let me jump
Martin,
into it. Yeah.
just one minute, one more detour right before we go into the demo. I mean, is this so? You've been involved in this space for a long time now. You're a research scientist.
Yeah.
Is this stuff still mind blowing to you? Because when you describe it to me, just now, and other times that I've heard introductions to quantum computing, to me, this just feels like a magical new world that I've stepped into. Is like, is this how does it feel to you after being in the field for so long? I know that's kind of an open-ended question.
Yeah, kind of open-ended, but in a nutshell, yeah, in full honesty, I feel you get very used to it. And what is special, obviously, now is I think it's a very special time for quantum computing now that these machines become available, even if it's really very early days. But maybe that's also what makes it very, very exciting.
Awesome, thank you. All right, on with the demo.
Okay, great. So what I'm showing you here is the Amazon Braket landing page in the AWS console. Comes with some information how to get started, shows you a little bit how it works, so the core building blocks, the modules that we offer on a high level to build quantum circuits, to test them on classical compute, to run them on quantum computers, and then post-process and analyze your result. Comes with information on pricing and additional links on the documentation and FAQs. I recommend to take a look to get started. Then obviously an interesting tab here are devices, and these are now the quantum computing devices that we offer to our customers as of today. We have one cloud-based managed simulator that's classical compute that emulates a quantum computer. And then we offer 3 actual QPUs at this point in time. There's a quantum annealer by D-Wave. I'm going to run an example for this one. There is an trapped ion-based machine, IonQ, and a superconducting machine from Rigetti. And if you click on these, you find more information on the number of qubits. And for example, what you see here is the actual topology of the chip. So this really shows you how the qubits lie on the actual chip, and the gray bars shows you the connections between these qubits. So then a natural point to get started for our customers would be to click on notebooks over here and just create a notebook instance. You can give it a name. You can choose a notebook instance type depending on your needs for your workloads. And then it will spin up a hosted Jupyter notebook with our own SDK pre-installed. So you can really, with one click, you can get readily started and build your circuits and run them against different backends. But what I want to show today is that you can also interact with the Braket APIs from any of your preferred local IDEs. So what I've prepared here is, so this is my Jupyter file system on my local laptop here. So we can hit these and work with these APIs just from our local machine. So let's get started with the first notebook here. Just a couple of boilerplate imports that I don't want to talk about here in detail. Then we set up an S3 bucket where all the results of our quantum computing simulations and runs will be stored. So if you get onboarded to Amazon Braket, by default, it will create a bucket that is called Amazon Braket and have your account ID in it. That's the one that I'm using it. And now let's just get our hands dirty and build the very first quantum circuit. So the gate set that we support with our SDK at the moment is listed here. So these are basically the core Lego building blocks that we have that we offer to our customers. You can stack them together. So one example here, a very paradigmatic example, is a so-called Bell state. It's just very simple, 2 qubits. And now we apply this Hadamard gate to the first qubit and then a CNOT gate between the first and the second qubit. So what happens is we first tip the first qubit into the plane. So it's in a superposition between 0 and 1. We haven't done anything to the second qubit. So now we are in this quantum state. Then we apply a CNOT gate that flips the second qubit if the first qubit is a 1. So nothing happens to this state, but we flip here the second qubit to 1 because the first qubit was in 1. And really, to do this in practice is very simple. With this simple syntax, it's just one line. So we instantiate here a circuit object. We call it Bell. And then we attach a Hadamard gate. We apply a Hadamard gate to qubit 0, followed by a CNOT gate between qubit 0 and 1. We can print this circuit to make sure it really coincides with what we had in mind. And then we can now run this circuit against different devices. So let me first use the local simulator that comes with our SDK, meaning this runs locally on our laptop. The advantage being obviously low latency, so it really allows you to do quick and dirty small experiments. It is free of charge, and you can work anytime, you can work offline. Then to run the circuit, it is really just this one line. So device.run, and we insert here, we pass this Bell circuit, and we ask for 1000 measurement shots, and then we want to retrieve the results. So let's run this here live. It's already done because it's a small circuit. And again, we see, as expected, the smoking gun of a Bell state, about a 50-50 split between 0, 0 and 1, 1 and 1, 1. So perfect correlations between the two qubits, the kind of smoking gun here for the Bell state of maximally entangled state between these two qubits. We can then move on and use a cloud-based simulator, where the advantage is now that we really are not bound anymore to our local machine, but we can really fully leverage the AWS infrastructure, in particular, use elastic compute to run many multiple circuits in parallel, and store automatically all results reliably in S3. So the only thing I have to do now is to redefine my device object, and I now set it to use our cloud-based simulator. So now again, it's device.run. I run the very same circuit now in the cloud. So this takes a little bit longer because obviously there's a little bit of latency till this is finished and comes back. But obviously, when you run very large circuits, this will not be the bottleneck of your overall timing budget. Again, the expected results. Now, every of these execution, this is what we call a quantum task. It comes with basically a unique identifier, an unique ID, ARN. So I can grab this and go into our console, filter by task, look for this ID, even days, weeks later, whenever, and find all the information related about this task here in the console. Again, I can also pull all the results stored that are associated with this task in S3. So everything is stored reliably here and not lost. Now let's get to the interesting part here and actually run this on quantum hardware. It is very simple. We just redefine again our device object. Now let's use INQ and call then basically device.run on INQ with the very same circuit. So nothing else required from your end. And we can check the status of this job, which has been created and is now in the queue. These are they're very scarce resources, single-threaded machines, so it's in the queue. While we wait for this to be completed, we can always take these unique identifiers, this ARN, to later recover a task. That's what I do with another IonQ task that I've run before. Let's just recover that and then analyze the results. So by now it has been completed. 1,000 shots were taken on IonQ. We see it's not perfect. It's not exactly the same what we had with the classical noise-free simulator. And that is showing you the state of the art in quantum computing. We have to deal with noise and this and decoherence. So there are imperfect results. That explains why we also have some counts here in 1-0 and 0-1 that we would not expect under ideal circumstances.
Before we go into the next example, could we at least just like explain a little bit about those challenges? So, because I described before, like I can't even imagine the difficulty of running a quantum system, given what I know about the challenges of running classical systems. You mentioned decoherence and some of this. I don't know if it's uncertainty, what have you. Could you just very briefly talk about some of the challenges that, let's say, like IonQ and some of these other hardware providers are actually working to tackle on behalf of anyone that would have to do this themselves?
That's right. As I said at the beginning, there are major scientific and engineering challenges out there. I just briefly mentioned decoherence. So what that means is, and that's a very important one, what that means is that we talked about that quantum qubits encode information like, compass needles that are allowed to point anywhere on the globe. But now let's say there is some undesired magnetic field, maybe the Earth magnetic field, that will influence this compass needle. So it starts to shake, and obviously you will, decohere and lose information because of this undesired effect, because your needle is not pointing to the location anymore where you wanted to have it. That is one of the biggest problems. So really, that explains to you why, for example, this ion trap machine sits in ultra high vacuum, shielded from all undesired effects. We have to take care of Earth magnetic field potentially, etc. These kind of things, simply because these systems, these are really single atoms, single ions, and they are very, this encoding of information is very fragile.
Awesome. Yeah, thanks for that. I know there's a lot of people that have worked with sort of on-premises sort of systems themselves that have faced a lot of traditional computing server management problems or infrastructure management problems, and what you're describing with decoherence is just like another level of challenges that most people, again, like you said, the research is evolving, right? There are no perfect answers to this, but leave that to the experts that are managing those back-end hardware providers.
Right. So then let's just move on with a little bit more advanced example. It is basically the many qubit version of the Bell state, the so-called GHZ state, which plays a very prominent role in many quantum computing protocols, in quantum sensing. The circuit itself is also very structured. It has basically the same structure as the Bell circuit. It's just an extension thereof. Again, you apply the Hadamard gate to the first qubit, and then a series of 2 qubit CNOT gates between these nearest neighbor qubits. So to this end, we define a simple helper function that, using Braket, creates a circuit object, applies a Hadamard to this qubit 0, and then a series of CNOT gates in this for loop. So let's just, for concreteness, take an example with 10 qubits. Again, we can print the circuit. This is what it looks like. And run this on the local simulator, again, very simply calling device.run and passing on our circuit. And in fact, what we see is the smoking gun of a GHZ state. You see we have 10 qubits here. In principle, there are 2 to the 10 potential bit strings that could come out of this. But for this highly entangled state, the only ones that we get is that either all qubits are in 0 or all qubits are in 1. And we have about a 50-50 splitting between
the world. So
one advantage of the managed cloud simulator I wanted to highlight here is that we can obviously now run very larger circuits. I'm going to run now, GHZ states between 25 and 30 qubits, and I can, using elastic compute, I can run them in parallel. So now basically I submit a task for 25 qubits, 26 qubits, 27 qubits, etc. They are created, and now they are starting to come back. You see all of them showing the smoking gun signature of the GHZ states. So this obviously helps you improve to quickly iterate and make experiments if you can run many of these tasks in parallel, as we have done here. This concludes the first part of my demo. Now I wanted to come back to something that we discussed briefly at the beginning, the analogy between these new family of hybrid quantum algorithms and deep learning. So these hybrid quantum algorithms essentially are embedded in a larger classical computation. So they work as a co-processor in tandem with a classical computer, a CPU. The idea being that you only leverage them for very short bursts of the calculation, and thereby trying to efficiently limit the effects of undesired noise and having parts of the computation done on the classical computer. So this is really reminiscent of what happens in deep neural networks, where typically you say you have some objective function you would like to find the minimum of, say the error on your training set. So we typically start out with some random guess for your parameters. This defines your neural network. You then execute this, this computation on the specialized hardware, the QPU, which does what it's best at, namely matrix multiplication, and then passes back this objective function to the CPU, which then takes the next educated guess for these parameters in a for loop until your algorithm converges. And exactly what happens here in these new hybrid variational algorithms. So what I showed you so far, essentially we had these single qubit and 2 qubit gates, and they were essentially hard-coded instructions. But the idea being here is that they take in some parameters, but leave it to a classical CPU to find the optimal values for these parameters.
This is super interesting because you know, I do a bit of work with AI and ML, and this not only the visualization you show machine learning on there, but something that felt similarly sort of new to developers as a paradigm and these sort of models was when TensorFlow first sort of came onto the scene, and folks had to learn how to sort of operate with this computational graph model. You had to sort of understand the DAG, the direct acyclic graph. You sort of construct the whole graph, and then the training phase is essentially just executed with like a graph.run or graph.fit, let's say, method. And it's quite interesting because these experiments or these tasks in the quantum world seem quite similar, even if those graphs look a little different. They use quantum circuits. They don't use bits. They use qubits. It's and maybe that's why you alluded before that these can become quite similar in some of the ways that they approach these problems.
Yeah, and actually our hope is that we attract a lot of interest from data scientists, machine learning experts, deep learning experts, who potentially don't have a formal background in quantum computing, but they will we think can very quickly pick up on these kind of concepts because there are these very strong similarities. And with Amazon Braket, we think we can make this sort of learning very easy.
Martin, we have a question in Twitch chat. Is this quantum sim or connected to a real thing?
So you can do both. As I tried to explain previously, it's really just changing one line of code, redefining the device object, and then you can either run your code on a quantum simulator or actual quantum hardware.
Awesome. So why not both, right?
That's right.
And I would say that makes sense, right? Like, let's we haven't talked about pricing, but I'd imagine that if you could sanity check, let's say, the task that you want to run and make sure that at least in the simulator locally it's working before you go and deploy that and potentially have an expensive mistake,
Exactly.
That in AI ML it works that way. Maybe you run your training and just make sure that it's not getting an out of memory error, but you're not gonna let it sit there for 50 epochs. And as soon as you know, all right, yeah, this will work as I understand, then you go and deploy it and scale it up to the quantum backend.
That's exactly the spirit. Yeah.
Cool.
Yeah, and I just also wanted to part clarify, part fact check, but the hardware that we're talking about here, they're not kind of all apples to apples, right? They have different capabilities and different workloads that you would run on each one of them, right?
Mm-hmm. Yeah. So what we offer with the 3 quantum backends today is a quantum annealer by D-Wave. The demo is yet to come. And this is a different paradigm from the one that I'm showing you today, which is circuit-based. You know, circuit, this is a quantum circuit, how we typically draw these. And IonQ and Rigetti are circuit-based machines. So as an input, you give them a quantum circuit, and that's what they would like. That's what they can execute on. I mean, physically they are very different, and they have very complementary, advantages and disadvantages. So, for example, I mean, Rigetti superconducting chips are very fast, but typically you only have only nearest neighbor interactions. Ions are typically have a slower clock rate, but these are really very pristine, high quality qubits, which offer all-to-all connectivity. And so what you can do as a user here is, you just, you build your circuit, you build your quantum algorithm, and then it's just about changing one line of code to compare the results from these different approaches to quantum computing and see what fits best for your particular use case.
Love it. You're making me sound right when before I said we meet customers where they are. We don't prescribe. We want to be able to offer them the options that they see out in the world. So just making me look good, Martin. You said the forbidden phrase before about undifferentiated heavy lifting.
Yeah.
It's wonderful. You're a great guest. You're doing all great work. So that was, you showed us the circuit based solutions there. You did mention quantum annealing. I think if I remember correctly through D-Wave. How is that different? Is there any way you could show us what that looks like comparatively to circuits?
Let me very briefly finish this here.
Okay.
Just a very quick walkthrough. So what we do here is we make a specific ansatz, a circuit which takes in some parameters, and with a classical CPU, you try to optimize these angles or these weights. The specific goal that we set out here is a graph coloring problem. Now, this may look like an academic exercise, but actually turns out that you can map relevant problems like, for example, portfolio optimization in finance or clustering in marketing on this type of problem. So what it means is I have this graph here with blue nodes and some edges connecting them. And the goal is to color every node either blue or red, meaning, for example, is this customer here in segment A or segment B, in cluster A or cluster B. And you score a point whenever you have an edge connecting a blue to a red dot. So that's an optimization problem, a combinatorial optimization problem. And we run this here using the specific ansatz, QAOA. It is a circuit. You can relatively quickly define the circuit, and it takes some parameters. And given these parameters, we then build the circuit. And these parameters are, first we can again print the circuit for a given set of parameters, has 2 qubit gates and single qubit gates. And then we run a training method here that will take as an input a specific device you would like to use. And then it goes back and forth between the classical optimizer and the simulator or the QPU backend until the algorithm converges and gives you some solution of red and blue nodes. So let's quickly visualize these. That's the solution that the quantum algorithm has come up with. Some of our customers are, in the blue segment, others are in red. That's the final solution that the simple toy model example has come up with. Obviously, you don't need a quantum computer to solve this, but we can benchmark here against classical simulations and convince ourselves that the quality of the result is the same. Now, what's interesting with Braket is that this broad problem family of graph coloring problems I can also run with D-Wave. So again, that's the last part of my demo. Again, some boilerplate of packages I need. I set up my S3 bucket, and now I set my device backend to the quantum annealer by D-Wave. Here, this machine does not expect a quantum circuit. It essentially expects a matrix that encodes our problem. So here we take, again, in this case, a graph with 5 nodes and some edges connecting them. The full problem formulation is this simple dictionary that encodes essentially the weight of these edges. And then the main code are these 3 lines. So we set up the device, which is a sampler. That's because D-Wave essentially samples from the low energy subspace or the kind of most likely good solutions. We then put this into an embedder. Embedding meaning we put this problem on the D-Wave graph. The D-Wave machine has a very particular physical structure. It's called a chimera graph, shown here. It consists of unit cells with 8 qubits each, and these highlighted connections between them. So the embedder helps us put this problem on this particular graph, and then we just call for a response with sampler, sample this QUBO problem, QUBO meaning quadratic unconstrained binary optimization problem for this given Q matrix. So let's just run this. This now goes into the cloud, runs on D-Wave for this particular problem. Now it's done, and this is the result for this graph coloring problem. So it suggests to color some of them blue, some of them red, and again, here you see you score a point whenever we connect a red to a blue node. So we score here, we score here, we only have to take a hit here, and actually we have to take a hit here because if we color this red one, we would take a hit here. So that's the optimal solution with an energy of -5 and the optimal cut size for this simple problem. The upshot being, again, we can now use different technologies to solve problems. In that case, a quantum annealer for the sort of problem that we attacked earlier with these hybrid circuit-based quantum algorithms.
This is super interesting. Graph theory was my favorite class in school, and remembering a lot of the methods I learned, which I guess were inherently classical for solving these problems.
Yes.
It is so interesting to see this done in a quantum manner, and I can't even imagine sort of the way that those algorithms look, because the classical computing algorithms for some of these graph solving problems are complex and hairy enough. So this is I'm geeking out. Sorry, this is really cool. Your point before about graph coloring problems or graph problems broadly being applicable is, you can't undersell that. Like, data exists in graphs much more than most people think. So you have the traveling salesman problem, you have the Knight's Tour, exactly. you have lots of different fun problems that real world problems can be modeled as, and I think we'll have you talk a little bit about some of those, or at least a little bit about what the Quantum Solutions Lab does on the tail end after you end up talking about. Actually, no, this was the quantum annealing example, right?
That's quantum annealing example. So cool. The demo, we are done with the demo for today.
Awesome. Yeah. So just connecting this these kinds of graph problems, maybe you could talk a little bit more generally about the complexity theory. The complexity classes that we have, and talk a little bit about the class of problems that quantum computing in theory could speed up. Is that something that you want to take a quick minute to address?
That's a tough one for a quick minute, but so you see this problem, for example, is an NP-hard problem, where essentially the problem is, you see, as the number of variables increases, the number of potential solutions increases exponentially, right? It's 2 to the, you have 5 nodes here, so there are 2 to the 5 candidate solutions, 32. If I add just one node, then it's 2 to the 6, 64, and it goes up very quickly, exponentially. That's basically the problem. The very basic promise that quantum computing here brings to the table is the superposition principle, namely that as classical compute runs out of steam because of this overwhelming number of candidate solutions, is using superposition is that it can basically scan the entire solution space in parallel, being in a superposition of all potential candidates. And then you have to play some tricks that's a little bit too advanced here to sort of amplify the amplitude along the best possible solution.
Yeah, and my understanding is that, or at least what I've heard is, some of the ways certainly that we do network security, for example, rely on the assumption that these problems stay hard to solve, right? Mm-hmm. So I think a good one would be prime factorization.
Yeah, so I mean, this is what sort of kick-started the whole field early on with Peter Shor in the 90s, showing that there is an exponential speed up in factoring very large numbers. So this seems very academic, but it's essentially the mechanism behind, you just said it, behind RSA encoding, behind security. And a quantum computer could just crack these problems very efficiently in minutes that just would take the age of the universe on any supercomputer. But the caveat, I have to be very clear about this, is yes, this kickstarted the field, and we want to be there to unlock these exponential speedups, but this will require effectively to fully control hundreds of thousands or millions of qubits, and that will be a long road with many scientific and engineering challenges along the way.
Mm-hmm. And like you said, well, I mean, what we saw with the D-Wave machine at least was 2048 qubits, right? Are we comparing apples to apples there?
No, not really. We should be careful. Shor's algorithm is designed for a circuit-based machine. And circuit-based machines at this point in time, these are universal quantum computers. They have very hard, very tough engineering requirements. That's why they are in the regime of 20 to 50 qubits or something like that. The engineering requirements for quantum annealer are more relaxed. That's why physically they have 2,000 qubits, but it's not in a sense a universal machine that you cannot readily run, like, for example, Shor's algorithm on this annealer. It's more specific purpose, tailored towards the sort of optimization problems that we just discussed.
Okay, so are the IonQ and the Braket hardware examples of this general purpose quantum computer?
Yeah, exactly. Yeah.
And so can we compare the bits, the number of qubits that they can support in line with this problem of Shor's algorithm that you're talking about?
Yes, absolutely. So let's click on devices in the console, and it shows that IonQ as of today has 11 qubits, and Braket comes with 30 qubits. I want to emphasize here that we should not only talk about the number of qubits. That would be oversimplifying. It's just one dimension. It's the quantity. Quality is another important dimension. And there are discussions, fights about what's the right metric, etc. At the end of the day, I think the big milestone will be to show quantum advantage. So really showing quantum advantage in an industry relevant application.
So on the academic side, can you give us a peek at what the major hurdle is? I mean, you mentioned, if we could theoretically scale up one of these general purpose quantum computers to hundreds of thousands of qubits, then we might be able to, I hope I'm not misusing the term, but we might be able to prove some of the the predictions in Shor's algorithm, right? Is that what? But
On
what
the
is
theoretical side, I mean, I think once we have such a machine, it will probably unlock a gigantic scientific curiosity and new inventions. But obviously, we don't want just to run Shor's algorithm, right? If we have, theoretically speaking, such a machine. So we also have to make the, contributions, developments on the algorithmic side. There are some other ones, for example, Grover algorithms that can give a quadratic speed up to search problems. But really, it's just a few ones so far, and we will have to come up with other algorithms, new algorithms. I think the whole community will help. That's why we sort of, are very happy and excited to sort of democratize quantum computing and give it into the hands of everyone, of all of our customers, to help contribute to this scientific challenge.
Yeah, and that's a great segue. I know early on in the broadcast we introduced you as a research scientist at the Amazon Quantum Solutions Lab, if I remember that correctly. So now that we have all of this behind us, we're talking a little bit about trying to then, eventually build business relevant applications. Can you tell us a little bit about what the Quantum Solutions Lab is, and I guess namely, what you do day to day? Because you've acted as instructor and educator for quantum computing and showed us Braket, but what do the folks over at the Quantum Solutions Lab do?
Well, I guess part of my job is to act as an instructor. So really the main mandate of the Amazon Quantum Solutions Lab is to engage and work collaboratively in deep long-term research engagements with our customers. So the way we approach this is, we take a specific use case, for example, some optimization problem, and work backwards from there, building small quantum prototypes along the way, obviously build up the in-house expertise, knowledge around quantum computing with our customers, and to provide what is also one of our mandates of the Quantum Solutions Lab is also to provide a transparent view of where the field is today. And that is why we always try to benchmark the quantum computing results, these proof of concept studies, with state-of-the-art classical solutions. This could be machine learning, this could be HPC. So we always try to fan out also in these adjacent areas to provide a transparent view where the field is to our customers, and then together develop a match plan, a broader strategy around quantum, how to position themselves, and how to get quantum ready for the future.
Wonderful. So for folks that are looking to get started with Braket, I know it is now generally available. I think we have a link in the chat to the upcoming webinar that the team will be hosting. So if people are looking to learn a little more, get maybe hands-on with it, or see some other examples, I'm sure they'll be able to see those in that webinar. It's on August 24th at 10:30 a.m. Pacific. You can register through the link that we provided in the chat. Otherwise, Martin, anything else that we missed on Braket, quantum computing at large? I know there's only so much time in the broadcast, and you've done a great job of sort of getting everyone up to speed, us included. Rob and I definitely not quantum computing experts, but we've read some things here and there, so hopefully that helps to sort of stimulate the conversation a little bit. Are there any other resources we should point folks to about Braket?
Really, I think that the best way to get started is just, spin up a hosted Jupyter notebook here, and get yourself your hands dirty. This will spin up a hosted notebook for you, and then you can just readily run the kind of examples that I run with you today.
Wonderful. Well,
awesome. Yeah. Thank you, Martin. This is fantastic. I'm really excited about this, and thank you so much for the crash course in quantum computing.
Yeah, thanks for having me.
Awesome. Well, with that, concluding our first demo of episode 10 here at AWS What's Next. Again, joining us was Martin Schwitz, research scientist at the Quantum Solutions Lab, teaching us a little bit about quantum computing, Braket, and getting hands-on for us. We will be taking a very quick break, so hang tight. When we get back, we'll be talking a little bit about Amazon RoboMaker WorldForge. This is something that launched just this week. I won't spill the beans on what it does because we have a very special guest that will walk us through exactly that. So stick around. We'll be right back.